like to thank the organizers to invite me to speak here, particularly John and Chris. Thank you very much for inviting me to be here. It's a great conference, a beautiful building. Unfortunately, the organizers got the date wrong of this meeting because I missed Halloween. And I don't think that you guys who don't live in the US appreciate quite well enough what it's like not to be in the US during Halloween, because when you dress up and you go and knock on people's door in a different country, people stare at you and don't really know what you're trying to do. So Halloween is not transferable from the US anywhere else. It's a low, Thanksgiving and all that, we do celebrate, but Halloween doesn't work. So anyway, I'm dressed up today, but I missed Halloween. So they asked me to talk about the hurdles and opportunities when it comes to climate change modeling. And I'm not sure if this is a trick or a treat. I'm not sure what I'm supposed to do here. Let me touch on this. Can we turn down these lights maybe right up front here? I don't know if that's possible. So this is one of the IPCC take-home images. This is the world as we know it, and as you see here, climate change is happening right now. You can see that these early data here, the best data that are currently available, they do indicate that climate change is having an impact on temperature worldwide. The same thing when it comes to precipitation. We have seen an increase in precipitation in northern latitudes and a decrease in more southern latitudes. So climate change has an impact on both temperature and precipitation. And if we project that forward in time, this one here is for the later part of the 21st century. You will see that the warming will continue with these different concentration pathways. The same thing for precipitation. The extremes between wet regions and dry regions will become even more extreme. The difference between wet seasons and dry seasons will become more extreme. So this is not only happening, it will continue as you know it. And I decided to take 3 different examples and illustrate the kind of hurdles that we are up against in the public health field, try to link these climatic events with public health outcomes. And the first one will address the struggles we have with large variance and how to deal with the low signal to noise ratio. Then how do you deal with multifactorial disease patterns where we have complex interactions of different drivers, and how do you tease out these different contributions of different drivers? And then a very difficult question is also the question of attribution. How do you attribute a certain individual climatic event to certain health outcomes? So it's, I'm not sure if I'll be talking about the opportunities. I'll talk about the challenges. And this one here is an image that illustrates the challenges when it comes to precipitation and recreational water use. There is no surveillance system in the US or anywhere where we try to link impacts of climatic events with their real outcomes. So there's nobody who monitors people who go to the beach, if they get sick or not. So there's no surveillance system. So how can we go about that? So we set up a study in northern, the lighting is not great, in northern California and southern California. Is it possible to turn down these lights somehow? And we decided to look at these 2 populations in those 2 different areas because they're very different environments. If you see the Los Angeles basin here, it's a highly urbanized environment that looks from a satellite perspective very much paved over, and of course you will have all this runoff that will contaminate the waterways and the coastal waters. In comparison to the situation in Santa Cruz, which is not pristine by any means, but still it's much less developed and much less runoff. And so what we decided to do, we decided to look at the relationship between precipitation, as plotted out here in inches throughout the months, and link that with river discharge for these 2 big rivers in Los Angeles, and related that to the water contamination. This one here is coliform water contamination in the coast. And you see there's a quite nice correlation between precipitation, discharge, and water contamination at that particular site. So how can we look into that? And we decided to use surfers as sentinels for human health. So we basically use this particular population as an extremely exposed population because these are the ones that hang out in the water for hours on end. land. And we conducted a cross-sectional survey by exposure sampling by looking at these two different sites, Northern California, Southern California, and we compared an El Niño event to a La Niña event. So this is climate variability, an extreme precipitation year compared to a low precipitation or dry year. And you can see that the self-reported symptoms by these surfers that get exposed to coastal waters spike dramatically in the rainy season during this particular year. Any symptoms, fever, stomach pain, gastroenteritis, and so on, and much less so during the dry years. So this OR stands for odds ratio, which is something like the relative risk that tells you that there is an elevated risk for these surfers if they surf during the rainy season compared to the dry season. The question is, how do you extrapolate it from surfers to the general population, right? So there are obviously differences between surfers and the general population. So I had a PhD student who I sent to every single beach in Southern California. Great job, by the way. There are 67 beaches in the 350-kilometer stretch between Los Angeles and San Diego. And this individual went to every single coast guard, beach lifeguard, and collected all their data of how many people attend the beach and how many of those go into the water. And you can see that there's something like 100 million people a year that go to these beaches with a spike in the summer, and 50% of those go into the water, so they have actual water contact. So now we know how many people get exposed. And then we dove into the literature, and it turns out that there are two concentration-response relationships that have been developed. One by a British randomized controlled trial from the 90s, done by David Kay, that shows this very exponential relationship between the risk of illness against contamination in the water, enterococcus level, so it's bacterial contamination in the water. And you can see that there's an exponential relationship when the concentration gets worse. You see more and more illness. And the Cabelli study, which is a prospective cohort study done in the US in the 70s, it's pretty much a flat line, but again, a concentration-response relationship that now allows us to link how many people go into the water, and if they get exposed, are they going to get sick based on this relationship? And this is what we found. We found that in the summer months, the majority of the people here peak, there's a summer month peak of gastroenteritis or diarrheal diseases, although the risk is the highest in the winter because that's when the exposure is the highest, but few people go swimming in the winter, so that's why the peak of actual events is actually higher in the summer. And if we compute the numbers, you can see it ranges something between 700,000 and 4 million, so there's a huge range depending on the model that you use. So where does this take us? We are now able to develop a model between precipitation and coastal water contamination. So we know that if it rains, we can model the enterococcus contamination in the coastal waters in Southern California based on this relationship. And if we now overlay climate change on top of that, we know that there will be something like a 4 to 16% decrease in precipitation in Southern California. So now we have how many people go into the water, we know the relationship of if they get exposed, how sick do they get, and if you see a decrease in precipitation, we can compute that potential risk. And you can see that we project a decrease in enterococcus level over the next, the 21st century. You can see here the contamination level will go down due to the fact that there will be less precipitation in the next century, although the variance will get bigger. You see the box plots here will get bigger, so there will be a higher variance. And if we then plug that into our concentration response relationship, we will get these numbers here. And I'm glad that you can see these numbers. In fact, I gray them out, because to be honest, I don't know what these numbers mean. We basically have to reach the limit of our modeling capacity because we have so much variability in our climate model, we have so much variability in our health model that we will generate numbers that you and I can't see or understand. right? These numbers, I'm not sure if they make sense, right? They range from 3 million to 18 million. I don't know what this means. So basically, we reach the limit of our modeling capacity with this kind of an approach. And so obviously, there is an issue here. So there is a positive association between measured precipitation or observed coastal contamination. And our data predict here a decrease in precipitation and a decrease in contamination of the coastal waters as a result. However, the storminess will increase particularly towards the end of the 21st century, which will have implications for public health. We call it the first flush, when it's dry and then suddenly a rain event flushes all these pathogens into the water. We do expect public health implications as a result. So that's one of the challenges that we are struggling with in this particular field of recreational water use and then climate change. The second example is the West Nile fever case that is an extremely complex, convoluted transmission, a disease that's very complex and basically depends on a lot of determinants such as abiotic and biotic determinants. So on this slide here, you can see that West Nile fever is driven by the presence of susceptible birds, then the introduction of an infected bird. You have local amplification of that virus within that bird population. You need to have these competent vectors and mosquito vectors. And then you need to have the bridge vectors that feed both on birds and in humans to spill the disease over to humans, and interactions of pathogens with the environment and so on. So it's a multifactorial disease. It's a very complicated disease pathway. And we analyzed the situation in 2010 when there was a big outbreak of West Nile in Southeastern Europe. So this is an area for West Nile where we hadn't seen West Nile in the past. And you can see here Bulgaria, Romania, the southern part of the Russian Federation. So there is a big cluster of West Nile. And we decided to look at the climatic attributes of this particular outbreak. You can see the numbers of cases up here. We examined 60 meteorologic stations in proximity to that particular outbreak, and we basically ran some correlation analysis between that outbreak and the temperature. Here, this graph here shows you a 30-year deviation from baseline, from a 30-year baseline, when it comes to that particular outbreak in 2010. You can see a big spike over the statistical average over 30-year baseline here in Russia, Romania, and Greece. And we plug that into our model here, and you can see that there are strong correlation coefficients with a lag of 2 to 3 weeks in northern latitude countries. In more southern latitude countries like in Greece and Israel, that impact was more immediate. So the lag was 0 to 1 weeks of that temperature peak with the particular outbreak of West Nile. We knew that temperature was not the only factor. As I told you earlier, this is a very complex, complicated disease. And so we took the opportunity to examine the outbreak further when the outbreak continued in 2011, 12, and 13. And you can see how it spread here in the subsequent years in Southeastern Europe. And we developed a multivariate model that didn't just look at temperature, but at all kinds of other environmental variables. You can see that in our model, the temperature in July was a predictor, but so was the water index, the presence of West Nile in that district the year before, the presence of wetlands, the presence of an eastern pathway for bird migration and the population. So this multivariate model now has more variables than just temperature, because as I mentioned earlier, it's not just temperature. In fact, the presence of West Nile in that district the year before was in fact the strongest parameter in our model, but temperature plays a role also. So we were able now to take the July temperature for 2014 and plug this into this model. Actually, let me show you the area under the curve. We validated the model here with the area under the curve for 2012 and 2013, and you can see a pretty good agreement there for our model. And this one here is now the 2014 data. And we predict West Nile here in northern part of Italy, in Serbia, in Romania, north of the Caspian Sea. And if you compare that with true data, this one here is the actual West Nile fever outbreak as it has occurred up to October 23rd, 2014. You can see a very nice correspondence here between the data that we predicted compared to what is actually happening. So you can see here the West Nile fever cases in northern Italy, Serbia, Romania, and north of the Caspian Sea. So there's a quite nice agreement with our model, despite the fact that we just plugged a temperature now into our model. The next step then obviously will be to take that model that we have for 2013 and put the temperature for 2020 in there. You can see that here now we model the temperature forward in time for 2020 or 2050, and maybe it's easier to see it this way. And this one here is 2013, 2020, and 2030, and you can see just with temperature how this particular outbreak spreads in Southeastern Europe in relationship to temperature. We are now in the process to model other variables and put in population and the lambda factor into this model too, to trying to improve this model because it is such an complex disease. But we believe that temperature abnormalities are a driver in West Nile, although other factors are important also, such as the water index. And we believe that because it's multifactorial disease, long-term predictions are very difficult. And the last example is one that looks at the Baltic Sea and vibriosis. So this one here is the Baltic Sea. This is Sweden. This is Stockholm, where I live. Finland, Poland, Germany, all the countries that surround the Baltic. And it turns out that there's a particular bacteria in these coastal waters that starts to bloom if temperature exceeds 15 degrees Celsius in low salinity. And it can cause wound infections that can be fatal, gastroenteritis and septicemia or blood poisoning in susceptible individuals. In fact, a lot of cases happen during warm years in the Baltic. And it's not just one Vibrio, there are a number of different, this doesn't show that well, there are lots of different Vibrio cases that live in different types of habitats. Here, this is Vibrio cholerae, Vibrio vulnificus, parahemolyticus, in different parts of the coastal areas, depending on where you are. So it's a complicated disease, again, with different types of response, concentration relationships. You can see here different growth curves for the different pathogens. And it turns out that the Baltic has experienced a warming over the last years that is projected to increase, as you can see here with this projection here. And during the summer months, we exceed the 50 degrees Celsius threshold, and these bacteria start to bloom in the Baltic. Indeed, over the years, we have seen more and more cases of these Vibrio the warmer the sea surface temperature gets. So here, this is sea surface temperature on the x-axis against the number of Vibrio cases on the y-axis, and you can see that the cases go up. And over the years, there have been more and more of these types of cases, particularly in 2006 when there was a peak. We have now developed a tool that's available here on this E3 geoportal that's called the Vibrio risk model, where we monitor sea surface temperature and salinity throughout the year. And this one here again is the Baltic, and you can see that in July this year, the Baltic started to heat up, and this one here is the 26th of July. And this particular model now predicts a high environmental suitability for these Vibrio infections in the Baltic. And sure enough, as you can read here in this Finnish newspaper, actually I don't read any Finnish at all, so I've skipped that slide. You can see here that in Finland, they reported 4 cases of these Vibrio cases, right exactly as we had predicted with our tool that monitors the sea surface temperature and the salinity. And you can see that these individuals had exposed to that brackish water in the Baltic. We also sent out a message on our network, and we identified 38 cases in Sweden, all of which had exposure to coastal waters. compared to only 20 cases the year before. So there was a real signal here when it comes to these Vibrio cases. However, what does that mean with climate change? As I mentioned, the current climate looks like this, and with climate change, we expect that curve to shift to the right with more hot weather and extremely hot weather. But can we link all these cases of the extreme hot weather to climate change? Do you draw a 100% association between that? And I don't know the answer to that, and I don't know if anyone knows, but it's very difficult to extrapolate from a climate change event to clear public health impacts. It's very, very difficult to do. And so this is my second to last slide. Because of this because of anthropogenic climate change, we believe that there will be more of these events that will have a dramatic impact on public health, but it's very difficult to draw a causal link to those events, although it is possible to estimate the probability of risk of occurrence of certain weather events under certain climate change scenarios. So we can still say that there is a link there, statistically speaking. In the example that I showed you earlier with recreational water use, the signal-to-noise ratio is difficult. The variance in both climate and health model adds up to be very difficult, technically speaking, to draw clear conclusions. And the multifactorial nature of many of the diseases that we are dealing with poses significant challenges for public health, for long-term predictions. And this is the most important slide, the individuals that are involved in the beach study, in the West Nile fever work, and in the Vibrio work. And that's all I have.
Stay up. Thank you very much. We have just a couple of minutes for questions. I think in this case we'll take maybe just one or two questions, if anybody has one for Dr. Semenza.
So in the beach study, as the temperature increases, do you expect more people to go in the water?
Great point. That's exactly right. So that's one of these multifactorial issues where you have a big population change in California, where a large part of the population is projected to move towards the coast. Then it gets warmer. More of them are going to go to the beach. Because it's warmer, more of them are going to go into the water and get water exposure. So it's very complicated to predict how that's going to pan out in the long run. That's exactly one of the issues. Good point. I take the point.
Great. Thank you very much. So Dr. Semenza has started us off with 3 great examples of how we use observational data and epidemiologic tools to come up with a kind of a risk modeling framework based on observational data. Our next speaker is Professor Ben Zaitchik, an assistant professor from Johns Hopkins in the Department of Earth and Planetary Sciences at Johns Hopkins University. Dr. Zaitchik is going to talk to us about the kind of data sets that are available and the way that we can pull different kinds of data together to do this kind of modeling. So, Dr. Zaitchik?